In this lecture, we are going to discuss the force between two parallel infinitely long current carrying conductors. For this, we will take first conductor PQ, in which current is flowing in upward direction having magnitude I1. The another conductor which is parallel to previous one, RS, in which also the current is flowing in upward direction. These two are separated by a distance R. So the magnetic field due to PQ on RS is pointing inwards. The direction of this magnetic field B1 is calculated by the right hand thumb rule, in which our thumb will be pointing towards the direction of I1 and the rest of hand will be at a point where we are going to find out the magnetic field. So if you apply right hand thumb rule, your palm will direct you perpendicularly inwards. So that's how we find out the direction of magnetic field at any point due to a current carrying conductor. The force on this conductor RS due to PQ will be in the direction of PQ, which is represented by F21. So the direction of this force, it is calculated by Fleming's left hand rule. So on applying Fleming's left hand rule at this wire, the magnetic field is pointing inwards, current is in upward direction. So if you apply Fleming's left hand rule, the force on this wire comes out to be pointing towards the wire PQ. Next, similarly, the direction of magnetic field on PQ due to RS, which is represented by B2, it will point outwards, perpendicularly outwards, and the direction on this wire PQ will be towards RS, which is represented by F12. Now talking about the magnitude of magnetic field and force. So first, the magnetic field on RS due to current in PQ is B1 is equals to mu naught I1 upon 2 pi r. If you remember, this formula came out from Ampere's circuital law, the first application of it. The B1 is the magnetic field due to this wire. So there will be the current I1 flowing through it. That's how this I1 came, and we are finding out the magnetic field at a distance small r. Next, similarly, the force on this wire F21 will be equals to B1 I2L sin theta, which again comes out to be mu naught I1 upon 2 pi r I2L sin theta. So this came from here, the value of B1, which we have already previously calculated, and the angle between this length of this wire RS and magnetic field on this wire. So these two factors are perpendicular to each other. So the value of sin 90 is 1. Next, F21 comes out to be mu naught I1 I2 L upon 2 pi r. B1 acts perpendicular and into the plane of the diagram by right hand thumb rule, which we have already discussed. So the angle between L and B1 is 90 degree. Next, the force per unit length on wire 2. Here the wire 2 is this wire RS. So the force on this wire, force per unit length, will be equals to mu naught I1 I2 upon 2 pi r. From this expression we have calculated force per unit length on this wire. Similarly, the magnetic field on PQ, the magnitude of it will come out to be B2 is equals to mu naught I2 upon 2 pi r. Next, force acting on PQ due to I1 through it comes out to be F12 equals to mu naught I2 upon 2 pi r I1 L sin theta. This value mu naught I2 upon 2 pi r was from here the previous expression, because F12 equals to B2 I1 L sin 90 degree. Again, the angle between B2 and L, this B2 which is pointing outward, and any elemental length on this PQ the angle between these is 90 degree, which again can be simplified to F12 is equals to mu naught I1 I2 L upon 2 pi r. So if you closely look at this, the expression for force on these two wires comes out to be equal in magnitude but opposite in direction. Also, force per unit length of the conductors, it is also same in both the cases. F upon L is equals to mu naught I1 I2 upon 2 pi r. So this is the important expression which is usually asked in CBSE examinations. Proceeding. So as a summary, we can say that if the current in both wires are flowing in same direction, then by Fleming's left hand rule, the force experienced by these two conductors will be towards each other, and hence they attract each other. And if the current of these two wires are in opposite direction, then the force acting on these two wires will be a repelling force, that is in opposite direction. One more definition is asked here, the definition of Ampere. Force per unit length of the conductor, which we have already derived, came out to be F by L is equals to mu naught I1 I2 upon 2 pi r Newton per meter. So if you put the values of I1 and I2 be equal to 1 ampere and value of r be equals to 1 meter, from calculation you will get the force equals to 2 into 10 to the power of minus 7 Newton per meter. Hence, the definition of 1 ampere can be defined as, it is the current which, if passed in each of two parallel conductors of infinite length and placed 1 meter apart in vacuum, causes each conductor to experience a force of 2 into 10 to the power of minus 7 Newton per meter of length of the conductor. So you have to remember this definition, it is frequently asked. Next is the representation of magnetic field due to parallel currents. In first case, the current in both the wires are flowing in same direction. So if there is a point in between these two wires, closely looking at this point, you see that the magnetic field due to this current I1 is perpendicularly inward, and magnetic field due to this current I2 will be perpendicularly outwards. So at a point in between these two wires, the magnetic field are opposite to each other. But in case the current is flowing in opposite directions, the magnetic field due to this I1 at a point in between these two wires is perpendicularly inwards, and magnetic field due to this current I2 will also be perpendicularly inwards. So at a point in between these two wires, the magnetic field will be in same direction in case the current is flowing in opposite. So that's it for the topic. We have discussed all the things which are asked regarding this topic. So thank you so much. Stay safe.